Time again to get started. Back to our optics. Let me give you kind of a quick summary of the next, I guess, really 3 days. And this week, I guess, is what I really want to say is, as you know, we moved the test from what would have been this Thursday till next Tuesday. And so we're going to spend these next 2 days and our last 2 days on optics and just see how far we get. And we'll get pretty good coverage of material, about the same as we've got in every other semester in the past here. And so we're about to put closure to chapter 35 and about to open 38, and we've got 3 topics to mention in there. And that's kind of our goal then, is to finish up our optics, and I should say our wave optics, because that was kind of that transition between chapters 35, 36, which were geometric optics, and then chapters 37 and 38, which were our wave optics, and we've been talking about waves. And so we're looking at some of the properties, and then that will be it to our introduction of optics. We'll have a test then on Tuesday. I'm sure Don will do a review. I forgot to talk to him this morning, but I'm sure we'll do a review on Sunday. And we should put that on the board on Thursday, and you guys can ask him and double check. Question.
Did he already put together a practice?
I don't think he's put it together yet, but after class we should go bug him, and he usually, starts putting it together. And usually people start asking him, well, tomorrow in lab, and so he'll have that practice. And anyways, that'll be the end of our optics, and then we'll go on to our final and 4th area of this semester, which is our modern physics. And so if I can draw your attention back to what we've been doing here, and I guess I'll just here put chapter 35, but we've been looking at light as waves. And if you recall, we started off with the double slit, and we said, let's take a look at light coming in. And the whole idea was that the light would spread out from one opening. It would spread out from the other opening. Somewhere on the screen, then you would get a pattern. And we talked about that pattern, how it was the interference of 2 beams. We spent a long time talking about that and what I would call derivatives of that. We put in mirrors, we put in lenses. If you recall, after that, our last lecture, we had these thin films. We said, okay, let's take a thin material. It could be made out of glass or plastic. I think oil was one of our examples. But the point is that if the light came in, it would reflect off the top surface. Then as it traveled through, it would reflect off the bottom surface. Of course, there would be other things going on, like this, and even more reflections and transmissions going on. But we said, let's take a look at the light reflected. Let's take a look at the light transmitted. But if you'll notice, we did exactly the same thing. And that's what I'm trying to say. We're going to do one more case, but it's one more case of exactly the same thing. It's going to take 2 beams of light and bring them together and ask ourselves, what would we see when those pieces of light came together? And I guess we'll relook at those 2 cases as we go into example problems in a few minutes. But the last one is an interferometer put together by Michelson. So we call it the Michelson interferometer. And let's take a few moments to talk about it, because guess what tomorrow's lab is? Yeah, you got it, the Michelson interferometer. And so we are going to hook up our optics. We are going to do exactly what we say and put them together, and you're going to look at these patterns. And so you can get a better understanding of the interference of light. We are going to set one up in lab. We're going to do the interferometer. You watched me do this last time in class with the glass wedge. And so what is the interferometer? Well, it looks something like this. Let's say we have a beam of light. I'll just put over here the light source. And so here comes our beam. Tomorrow in class, or Thursday, for those of you who have the lab on Thursday, it'll be basically this laser beam. You'll have a different model, but other than that, you'll have the red beam and you'll go shooting it off to the side. To get two beams out of this, we will then put a piece of reflecting glass right here. I'll call it a 50% mirror, meaning that as the light hits that surface, and we have two models, I'm going to let the light reflect off the front surface, but some of our models, the light reflects off the back surface, and in fact, I think we might just pull out the ones that reflect off the back surface. So let me draw it that way. I'm not 100% sure, because we have one of our models, we have a bunch of them, and that is probably the best one to use in lab, so you guys all have the same models. But some of our other models, we have just a couple of them. In fact, did I bring one out here? I was thinking about grabbing one. I forgot to grab one. But you'll see it tomorrow in class. It's pretty straightforward. You take a piece of glass, and when it hits this polished surface or partially polished surface, what's going to happen is the intensity is going to be split 50-50. And that's the key step I wanted to point out, because all of these, what we needed is the light separated into two beams. And so whether we let the light go to two holes, which gave us our two beams, or whether we let the light reflect off to surface, that gave us our two beams, this one does the same thing. It reflects off of a surface and divides pretty evenly at 50-50. We then put what I will call M1 for a mirror. This is what I would call a 100% mirror, although I suppose no mirror is completely 100% reflected. But it's a good quality, well-polished mirror trying to reflect all the light back. The same thing is going to happen over here. I'll call it mirror number 2. And the idea here is that we're going to try to reflect as much, if not all, of the light back as we can. But the point is that, like all of these, we can do a constructive and destructive interference. The beam's going to come out, hit here, bounce off, and come back. And when that beam hits here, it will split in half again. We won't even worry about the half that goes back to our light source, but let's look at the half of the half that goes forward. Likewise for the other mirror. For the other mirror, the light's going to come out, hit that reflecting piece, come back, hit here, and bounce off. Now again, half of it will go through and half of it will reflect off. And so I'll draw those on here, but as you'll see in the lab, this just goes back to our light source. We'll never even see this. We won't pay much attention to it. But if right here I put a screen, this is where the interference is going to take place here. Just like we did for the double slit, we can put a screen. We'll put a screen here. And notice the two beams are coming together. And so what would you see right there? That depends how these beams come together, right? Are they constructive or destructive? And so we can ask the same thing like we did with the thin film. What we can say is there is going to be a path difference. Now, of course, for the thin film, the path difference was just down and back twice the thickness. That was pretty easy to see. For the double slit, the path difference was d sine theta. For the interferometer, the path difference would be, well, one went this way, which we might call this length 1, and the other one went this way, which we might call length 2. Then the difference between them would be length 1 minus length 2. I guess technically it goes down and back, so I would have to double both of them. And even then it might even get a little more complicated, because if you look at this, doesn't the light change its wavelength when it goes through the glass? And so if you watch from the first split, this one went through the glass, bounced off, and went through the glass again. Whereas this one did not go through the glass at all. I mean, other than the original part through the glass, but then they were together, so it's not part of the difference. And so you may argue that L1 needs to be considered a little bit bigger in length. Well, here's where we're going to say, let's not worry about the total all length. We could go through a lot of trouble calculating what is the overall length, but I think you would agree there is some difference. Or, of course, we can set it up so that there is no difference. And that's how this interferometer works. And that's, again, what you're going to do in the lab tomorrow. One of your mirrors, and I think on this model, it's this one, moves back and forth. And we have a little adjustment screw, and we can turn it, and we can move that. Let's just say we move it by a distance of d. You see, if our path difference is an integer number of wavelengths, wouldn't we expect to get a maximum on this screen? That they would come back and add in phase? Isn't that what we kind of said over here? Didn't we say if twice the thickness was an integer number of wavelengths, although we said number of wavelengths in the medium, we would get constructive interference? Although we said that if there were no phase changes, right? All right, so you guys remember, I think, that same equation could give us minimums, could give us maximums. The same thing would be applied here. If the path difference is an integer number of wavelengths, then we would get maximums, or we could get minimums. It depends on how many phase changes we have. And so last time we drew our phase changes in red here. Let's take a look here. Now let me not repeat here because I didn't put any indices up there, but if you look at this beam that is coming and reflects off, right there it's reflecting from glass to air. It's a reflection, but it's a reflection off something of lower density, so no phase change. It bounces off and hits this glass mirror, phase change there. Then we're looking at the beam that goes straight through, and remember, no phase changes on straight through. Okay. The other beam comes across, goes through, hits the mirror, phase change there. Comes back, and there is a phase change there. Okay, so one beam goes under one phase change, the other beam goes under two phase changes. What does that tell me about my equation? Minimum, good. And so this equation would give me the places that there are minimums. The other equation, where the path difference is an integer and a half wavelengths, would give me my maximums. And so again, I hope you're seeing that as I talk about the interferometer, just like I talked about the thin film, just like I talked about the double slit, and just like we'll talk about chapter 38, it's all looking at the waves and how they come together. Is it constructive or destructive interference? And so this would be my set of equations for constructive or destructive. The truth is, though, for our work, we're not going to really care about how long the length is. We're just going to look at changes. And if this what is a dark spot on here. And so you look at the screen and you see a dark spot, and you move the mirror. As you move the mirror, it will change from being dark to being bright. And then if you move the mirror a little more, it'll change from being bright to dark. And so basically, if you move this here, and so you increase whatever this delta is by D, so let's say I move the mirror by D, D then, let's just say we move it from being bright on the screen to bright on the screen, or dark on the screen to dark on the screen, you'd see that whether we increase from dark to dark or whether we increase from bright to bright, it would be corresponding to an increased path difference of 1 wavelength. And I'll put a 2D there because if the mirror moves D, how far does the light increase its path? Twice as much, right? The light's got to go down and back. So again, if the mirror moves D, then the light increases by 2D. And if the spot I am looking at on the screen was already bright, and then it gets bright again, that must correspond to a distance of 1 wavelength. Or if it was already dark. So you'll see tomorrow when I give you directions, or if you have the morning's class and Don gives you the directions, he'll say, okay, you hook it up, and he'll go through the whole procedure. And there's a little bit of delicacy here in setting it up, because you can imagine we've got to get 2 beams to come together, and they have to overlap. And we're talking about overlapping within a wavelength of light. This is small. And so it is a little bit tricky here. Fortunately, the equipment is designed to handle those little distances, although I must say this is the only instructions in the lab manual I've ever seen where it says no cursing is allowed, and about halfway through the first paragraph. But it can get a little aggravating, especially in part 3, where you've got some fine tuning to do, and you got to get the light exactly to overlap within 1 wavelength. But once you do, then you can move the mirror. And the neat thing about this is, notice it could easily pick up subtle changes. Very, very, very small distances. And so that's what the interferometer is for. It can measure really, really small movements. If this mirror moved, let's say, 1/4 of a wavelength, what would happen here on the screen? Well, if it changed 1/4 of a wavelength, that means the down and back is a 1/2 a wavelength. That means if the screen was already dark, it would go bright. You could easily tell a dark to a bright. In fact, you probably could do halfway in between that. In fact, probably even better than that, you could probably do 1/2 of a 1/2. And so easily, we could pick up the movement of a 1/2 a wavelength. We could probably even do 4 times that. We could easily pick up the movement of 1/8 of a wavelength just by looking at the screen. And that's the neat thing about the interferometer. You could pick up movements 1/8 of a wavelength. And so that's not quite a 1/10, but let me call it a 1/10, because we already know wavelength is a couple hundred nanometers. 1/10 of that is tens of nanometers. And so movements of tens of nanometers are easily just picked up with something as simple as this. And that's the neat and the last interference one that your book takes time to talk about in this chapter. There's other interferometers. In fact, my favorite is the Fabre-Perot interferometer, but your author uses this one, and for good reason, because we're going to come back to this. There's a historical part of the Michelson interferometer that will lead us into relativity real soon here, and as we next, not 2 days from today, but 9 days from today, we'll come back to this interferometer and look at a very famous experiment done as we start our relativity. So with that said, let's put closure to this chapter. This is kind of where I was hoping to have gotten last lecture. We didn't quite make it there. But let's do some example problems here. And move into chapter 38 after that. So as I turn to the examples here, what page is this on? Let me get rid of this here. Need that later. But I put number 13 down here first, and got the PDF file there. If I can kind of roughly find the right page to go to. Chapter 37, number 13, page 1070. And so, learning to drive this thing better, 1070. Here we go. How about if we view it at 125%? There's number 13, and hopefully that's big enough to read here. Let's do this one as our first concrete example. Let me grab my calculator. Let me kind of clean off the board here. Oh, I should have got some water this morning. And say, all right, what is the double slit experiment? And so, not a surprise, you'll see that this first example is a double slit. And so what does it say here? It says in figure 5, I won't turn back to 5, but it is the double slit experiment here. It says let L be 1.2 meters, let D be 0.12 millimeters, and assume the slit is illuminated with monochromatic light about the middle of the spectrum, 500 nanometers. Calculate the phase difference between the two wave fronts arriving at point P when theta is 1/2 degree. All right, and so looking at this picture, I'll erase it and draw it a little bit bigger, but this is our double slit experiment. And it's looking at two beams of light, one coming from the upper slit and one from the lower slit. And so here's the screen, here is the double slit. Light comes in. We call this straight down the middle. Angle is 0. And so I've got beam 1 and I've got beam 2. And if you remember, then this is the path difference delta. This is d sine theta. And so they're asking us to look at a point P that is down the screen. And what did I read here for the angle? Point P is 1/2 degree. And so theta is 0.5 degrees. And it was degrees, not radians, correct? Yeah. All right, so small angle as it should be, which would tell me then the path difference being d sine theta would be what did they give me for d there? 0.12 millimeters sine of 1/2 degree. And so that little extra distance traveled is not much, but again, remember, the wavelength of light is not much. And so let me check which mode I'm in. Oh good, I'm in degrees here. And so 0.12 times 10 to the negative 3 times sine of 0.5 comes out to be a path difference of 1.0, I'll go 47, why not, times 10 to the minus 6 meters. Okay. Now that is a little bit bigger than one wavelength. So one wavelength in terms of phase is 2 pi. And so one wavelength, there would have been a bright spot down here. In fact, why don't I just say, what is delta divided by lambda? See how many waves lengths I have done here. So if I take that number and divide it by, and we were at 500 nanometers? 500 nanometers. This is just a hair over 2 wavelengths. So I do know this much from our discussion on the double slit, that there would be bright, maybe I'll change colors, 500, is that blue yet, or is green? Kind of, I'm going to call it blue.
Didn't we say L was the distance between the screen and the opening?
Yes. No, wait. The L is the screen and the slits, yes. I haven't used it yet. What is L? 1.2 meters? I'll put it on here.
Oh, yeah.
1.2 meters. So far I haven't needed it. I think I will before the problem's over, but okay. But I guess then down the center I would have constructive interference, no path difference, no phase difference between them. And then I would have another blue, let me center it up a little better. I'd have another blue one when the path difference is 1 wavelength. And the point they're asking me is actually 2 wavelengths further. And so we're looking at point P, that is one of the bright spots, or at least maybe just a hair past the bright spot, but pretty close to the second order bright spot there. And that's what this has told me. Although, again, that really hasn't answered the question that they want. They want the phase. Well, at this point, I kind of know it. I mean, it's 2 wavelengths, so each wavelength is 2 pi phase. So it must be 4 pi. Is that what they asked, the phase? Calculate the phase difference between them. Huh?
The number of path lengths divided by lambda is the order of magnitude, or like, how did you know it was on the third one?
I would call it the second one because the center one's 0, and then 1 and 2. Well, there's a couple of things. I did it more conceptually than I did mathematically. I'll repeat conceptual and then I'll do it mathematically. But I knew this was order 2 conceptually because I know that I get bright spots when the path difference is an integer number of wavelengths. And that's the path difference. And so I divided it by how many wavelengths to see how many by the wavelength to find how many I'm off by. And so I know I'm off by 2. So that means this extra piece, if I were drawing it in here, would physically look like 1 wave plus a second wave. I could get 2 waves in that extra distance. And that's why then for the rest of the distance they would be in phase. And so I would get in phase, but this top one would travel 2 waves further than the bottom one. And that means there's some other point here where it was 1. Now, if you also then want to see this mathematically, you can remember that path difference is d sine theta. And d sine theta is an integer number of wavelengths. So there's mathematically how you would say this is giving me the order. I can just take this little ratio and replace d, and then replace d sine theta with integer number of wavelengths and get the order m. So if you prefer the math, there it is. Which actually is a good discussion in itself. Not really answering the question quite yet. The question is, what is the phase between them? And so again, going back to the connection between the physical distances and the mathematical phases of a wave, we have the path difference is to the wavelength as the phase difference is to 2 pi. And hopefully you kind of remember that little derivation we did to find the intensity on the screen from the double slit. So path difference is to wavelength times 2 pi is my phase. And so that number I've already done. It's just a hair over 2. It's 209 times 2 pi. And so that would be the phase difference. And so 2 times 2 is 4. I'll put 0.18 pi if you like, but it's basically, oops, that's it. It's basically just 4 pi, 2 wavelengths. And so when I first read this, I thought, oh, this is a good one to kind of start looking at our numbers. Because it's got all the little neat pieces in it, yeah. What about the wavelength?
Divide by the wavelength?
No, I already did. This whole quantity is 208. And then moving on to B. B says, let's put ourselves on the screen 5 millimeters. Okay? And so I'll put B here. This was our calculation with A. And let's go 5 millimeters down. And when I go 5 millimeters down, then I will have something that looks like this. This distance, and I'm not sure if that is going to be at the same place or not. I don't know. It could be at a higher order or a lower order. It may not even be at a bright spot, maybe something in between. But I do know that if I take y equaling 5 millimeters, that the tangent of the angle is y over L, which is about the same as sine theta. So my path difference, which is d sine theta, is dy over L. And so this would be how much extra path I would have. Actually, it might be kind of nice to even pause partway between and just find theta. Now, that would help me answer my thought question of this 5 millimeters down. Is it at the same place or is it more or less? What is the angle there? So before I even continue on with path difference, let me just find the angle theta, even though it's not a direct question here. But y is the 5 millimeters, and the L is 1.2 meters. And so if I take the inverse tangent or inverse sine, whichever you want, but tangent I suppose is a little more accurate, I will get an angle of only 0.239 degrees. So this angle is clearly a lot less than here. This is 0.5. About half of it is about right, so I'm somewhere near the first order. It looks like it's a little bit less than half of it. And so I would suspect then that my phase is going to be a little less than 2 pi before this is all done. And so when I come over here to get my path difference, I'll get my path difference by putting in the value of d, y, and L. Or I can, at this point, just go d sine theta since I have theta. But I'll jump all the way to that one. And so my d, it was the 0.12 millimeters. My y, I just did y, what was it? 5 millimeters. And then the L is the 1.2. So we're looking at a path difference of 5 times 10 to the negative 7. And I guess I did an approximation there because that is exactly one wavelength. It's not just a hair under one wavelength. It is one wavelength. Because then if I write this as delta over lambda here, I got 5 times 10 to the minus 7, and 500 nanometers is the same as 5 times 10 to the minus 7, and so we're looking at a path length, one wavelength. And so in this case, we are obviously then looking at that point right there. And so this beam up here, even though it's blue, I'll change colors so it doesn't mix with the other one, but we're looking conceptually at that there is one extra wavelength in there. So to finish the problem, the phase then is to 2 pi as the path difference is to wavelength. So phi then would be 2 pi times 1, or approximately 1, and you're going to get 2 pi. And so the waves differ by 1 wavelength, 2 pi radians, yeah.
Where did you get the D? Did they give that to you?
Yeah, D, I didn't put it on the board here, but it's the 0.12 millimeters. It's right there. Yeah. And so there's the 0.2 millimeters. And I think there's a C to this one, is there? C, oh, and a D. Oh, what is the value of theta for which the phase difference is 1/3 of a radian? Okay. Maybe I can squeeze that in here. C. The phase difference now is 0.333 radians. And so I'm going to work backwards. It's too bad it's not in integers of pi because I can't do it in my head. So we're going to have to get the calculator out here. But phi is to 2 pi as delta is to lambda. And maybe I'll just get that number first. So 0.333 over 2 pi. So 1/3 divided by 6.28 is what? 0.3333 divided by 2 divided by pi equals 0.053. Well, that's not much distance. And I guess that makes sense. I mean, they're not even talking about one wavelength of phase, right? One wavelength of phase would be 2 pi. And so we're looking at some point on the screen that's right about there. And what are we looking at for? What is the value of theta? Okay, so this is going to be a small angle here, but this will allow me to get delta. So delta would then be this ratio, 0.053 times the wavelength. And the wavelength is 500 nanometers. And so we're looking at 2.65 times 10 to the negative 8 meters for my path difference. And of course, my path difference is equal to d sine theta. And so I can get theta here by taking this delta, divided it by d. D was the 0.12 times 10 to the minus 3. Then I can go the inverse sine of that small number and get an angle of only 0.012 degrees. And that, of course, fits my my intuition on this first one right here, that we are looking almost straight down the center. There's very little change to it. It's, only 1/3 of a phase, and remember, a whole wave is about 6. So, and so we're only 1/3 of that. So what is the value of theta? Pretty small. And then D, what is the value of theta for which the path difference is 1/4 of a wavelength? Now, again, I'm out of room here, but I think you're getting the point now of the problem, that all of these are tied together. The path difference, the wavelength, the angle, the phase between them. And so it's just a matter of how you phase the question. And in this case, we are looking at a path difference as a quarter of a wavelength. And so that is our path difference. What is the value of theta when our path difference is a quarter of a wavelength? And of course, the path difference equals d sine theta. So we can find theta by taking the inverse sine of lambda over 4 divided by the d. And so I've got the lambda over 4, I got the d, and I've got inverse sine. And so theta equals what? Well, our wavelength is 500 nanometers. Divide that by 4. Divide that by d, which was the 0.12 millimeters. And I get a pretty small number. I'll take the inverse sine of that and get an angle of 0.0597 degrees. Doesn't seem right. What did we get? Lambda divided by 4. No, I got 500 times 10 to the minus 9. But I 0.5 divide by 2 divide by 4. I guess I would have well, I guess that's about right. We said this was 0.5, right? So half of that, and then a quarter of that. All right. Okay. Yeah. All right. I guess that's not off. 0.06. Is that what you got when you get? Yeah. Yeah. And I'll just try this. We already know this was 0.5. So the first order would be about roughly half of that. I'll cut that in half. And we're talking then roughly a quarter of that. So I'll take a quarter of that. Yeah. And I get 0.06. So it seems small, but I guess all these were pretty small. And like I said, I thought that would be a good one to do. Again, let's focus on the double slit, but now let's go to the intensity pattern. Let's try number 21 here. 21 is a good problem here. If I go too high, it'll go off the screen. Huh? How high can I go? Ah, well, I'll stop there, right? And so 21 says we've got two narrow parallel slits. So here's our double slit. They're separated by, again, 85% of a millimeter. They're illuminated with 600 nanometers of light. The viewing screen is a little further, 2.8 meters away from the slit. What is the phase difference between the two interfering waves on the screen that is a point 2.5 millimeters from the central one? So that's a lot like what we did. But here's, I think, the more interesting one that we haven't done. It says, what is the ratio of the intensity at this point to the intensity at the central bright one? And so we can get to that intensity equation that we worked out here. But let's do A first. I'll kind of clear off the board here and say, all right, let's take a look at this calculation. And so what am I doing here? Number 21, we've got the double slit. We've got the screen. I'll put a little mark for straight down the center. And come back and read some of these numbers. The slit size, 0.85. So 0.85 millimeters is the value of D between the two slits. The screen, did I read 2.8 meters? Is that what I read over there? 2.8 meters, yeah. And then the light that illuminates it is 600. I'll put that on the board. Wavelength 600 nanometers. And we're looking at some point on the screen, either up or down or left or right, depending on how you have your screen oriented. But this one says, what is the phase difference between the two interfering beams or the two interfering waves when the screen, at a point on the screen, 2.5 millimeters. All right, so we're going to move down 2.5 millimeters on that screen. So again, I would do the same thing where I would say, let's look at that path difference. The path difference between the two beams is d sine theta. Now, sine theta is approximately tangent of theta, because tangent is the distance on the screen y divided by the length between them. And so for small angles, I'm just going to replace sine theta with tangent theta. And that will give me my path difference. I'll start there and get a number, but those numbers I have. D is 0.85 millimeters. Y is 2.5 millimeters. Divide by L, which is 2.8 meters. And so all of that together makes 7 I'll round it to 60. Yeah, maybe I better do 59. 7.59 times 10 to the negative 7 meters. And so I switched everything into meters and did my product and quotient, and so that's the path difference. I'm kind of curious how many wavelengths this is, and so I'll take that number and divide by my wavelength, which is a little smaller than that number, so it's going to be greater than 1 but not 2. And so divided by 600 nanometers, I get 1.26. So this is a little more than 1 wavelength, and not 1.5, but somewhere in there. So 600 would be, would be orange or yellow? I'm going to go with orange since I don't have a yellow pen. All right, so we'll call it orange. Yeah, I think it's more. Yeah. We know the sodium was very yellow at 589. But looking at my light coming in, of course, down the center, I would get constructive interference. And if I'm understanding this right, I am at a point that has a path length of a little more than 1 wavelength. So I would have another constructive interference right there. I would not get the second one until right there. So I'm between the first and the second. And I know it would go dark halfway between. And so had this come out to be 1.5, I would have been saying, hey, this is a dark spot. If it had been an even integer, I would say, hey, it's a bright spot. It's neither of those. It's something in between. And I'm not sure my picture up here fairly represents the equation we got. And so maybe I should redraw my picture for the intensity pattern. But we took some time, if you recall, to go through and do a little derivation of what is the intensity anywhere on the screen. Not just where are the bright spots and where are the dark spots, but what was the intensity pattern. And if you recall, we got this. We said the intensity on the screen would be the intensity down the center times a cosine squared of the phase over 2 between them. And so we should probably plot this a little more accurately, and maybe I'll do a blue color for that, but it would look something like this. It would be very bright and go dark and then be very bright. Then it would go dark and then be very bright. So we are at a location right about that intensity, if you will. So we are certainly not at the brightest place, otherwise this would have come out to be an integer. And we're not at the darkest spot, otherwise it would have come out to be an integer and a half. We're someplace in between all of that. Which is really the question for part B. Oh, wait. Did I answer A yet? I'm sorry. What is the phase difference between the two interfering ones? All right, so before I keep going into B, let's keep going with this. This has to be equal to phi over 2 pi. So to finish part A, which we are going to need for part B, which was the main reason I picked this problem to look at, is if I take that 1.26 and multiply it by 2, I'll just write it in terms of pi. That is 2.53 pi radians. So, as we suspected, more than 2, but not 3 pi. So that's the phase between them. So now I can get to the real question I wanted to address here is then, what is the ratio of the intensity of this point on the screen compared to the central bright fringe? And so let's do this. What is I divided by I naught? And it would be cosine squared of phi over 2. And so that is our intensity. And so I have my phase. And I still have just the number 2.53 in my calculator, so let me multiply it by pi. Let me then divide that by 2. And so this is cosine squared of about 3.97. Of course, it's in radians, so my calculator, I've been working in degrees, as you noticed for the last few times. Let me come down and change it into radians. And then I can go cosine of the answer. And then square it. How do I know if it's radians or not? Yeah. Well, I 0.453. I guess the best answer for that, and not the only answer, but at this point, the good answer is the units. What are the units for radians? Yeah, remember doing this in Physics 121? The definition of an angle, if you took a circle and you chopped it up, you might remember the ancient Greeks said, look, there's the arc length, there's the radius. They were looking at big circles and small circles, and so they wanted to realize that that angle would be the same on the big circle as well as the small circle. And so if you call this arc length 1 and radius 1, and this arc length 2 and this smaller one radius 2, then they realized by proportions that those are the same. And that's what they call the angle theta, and that is the angle as defined in radians. That's why if you took a full circle, the arc length of a full circle would be 2 pi r, divided by r gives you 2 pi. Right? And when you deal with angles in radians, then you're looking at a ratio of 2 lengths. That would be in meters, that would be in meters. What do you end up with? No units, right? So radians is not a unit. And so we often say, if it's real number, if it's only a number, if it doesn't have any units, it must be radians. And that's what I have here. When I did this step right here, I took path difference divided by wavelength. I have no units. This is just a number. And so I put in just a number. That means I'm in radians. And so I did it to myself right here. When I did this ratio, I was thinking of this in radians, right there, 2 pi. Right there, ratio.
Is that always going to be the case? Like divide by phi is always...
Oh, well, no, I could have gone phi divided by 360. And then my angle would be in degrees. and then I would put it over here in degrees, sure. So again, I did it to myself, and of course, I got to pay attention. It's been a long time since I said that, but you have the freedom of choice. But once chosen, it has power over you. So you had the freedom to get some sleep this semester, but you chose this class and probably a math class, and between those two and maybe another class, you're not going to get any sleep. And should have told you that before you signed up for class, right? So, but there's my second example. Let's jump down to 25. 25 switches us from the double slit ones to an example of a thin film. Well, let's take a look at that one. Here's 25. And hopefully what you got out of not just the double slit, but also the thin film, as well as the interferometer, that we want to look at the path difference between them and how they come together here. So if we read number 25 here, it says a thin film of oil, let me give the index, 1.25, is located on a smooth, wet pavement. When viewed perpendicular to the pavement, so in other words, we got some oil on the ground. There's a little oil. Maybe it was actually already there, which often happens is, you know, cars drip oil and then the rains come. Well, not this year, we haven't had any rains, but supposed to have rains. And maybe next year we'll have some rains here. But the rains come and then lift the oil off the ground. And so the oil comes out, and what you end up having is a small amount of oil floating on top of water. And I think as we pointed out, you get that little rainbow effect here. You get constructive interference for your different colors. So it says here, when viewed perpendicular to the pavement, the film reflects most strongly in the red. And they say the red over at 640. It also says it reflects no green light. And so they give us the 512 for the green light. How thick is the oil film? Okay, so if I was drawing a picture of that description here, I would have something that looks like this. Here is my oil film. I guess I would have air on top. I would have water underneath it. The index for air is 1. The index for oil is 1.25. The index for water is 1.33. Okay? And so as we were working out these films, this part, and the reason I picked this problem was, again, go through this logic. If I think of this thin film, which is made out of oil here, as a thickness T, ask yourself, what is the path difference? Well, down and back is twice the thickness. And your first reaction should be, if that is an integer number of half wavelengths, not half, integer number of whole wavelengths. And let me pause there. Integer of wavelengths where? Yeah, it's in the oil. Because as we draw what's happening on here, remember that down and bounces off the top. The second beam bounces off the bottom. This right here is the thickness of the oil. Down and back is the extra path length. What we are asking is how many wavelengths fit in there. And so we are asking how many wavelengths are in the oil. And so when we put an n in that equation, it could lead to some confusion if we're not careful about what n are we talking about. Is it the n for the air? Is this for the oil? Or is this for the water? And so we need to go back to, well, why do we even have a path difference? Why do we even have an interference pattern? And that's why, is because there is an extra path length in the oil. That's an important piece. Now, also, the second thing that makes this a little challenging is my first reaction would be to think that if that condition is met, I would get constructive interference. But that's not the whole story. Then we have to add the extra piece that I've been doing in red and looking at the effect of any phase changes that might occur during a reflection. And so now we come over here and ask, this would have given me maximums, but does it stay that way? Do I get a phase change for this first one that reflects off the oil? Yeah, so there's a phase change there. Is there a phase change for the second one, which reflects off the water? Okay, so there's one there. So each of them undergo one phase change. So the net effect is no phase changes. In other words, if there had been no phase changes, the two waves, one of them may have had a crest and the other one may have had a crest. But now with the reflections, they're each a trough. But either way, they line up together. So that tells me this equation is the equation that gives me maximums, and this is maximum for reflection. And the other equation is maximum for transmission. And so there's the question. What do I want? Do I want the equation representing maximums or minimums? Do I want the equation representing light that is reflected or light that is transmitted? Well, as I read into this, doesn't it say I want the reflected light? So I want reflected light, good. Do I want maximums or minimums? Kind of looks like both. It says the red is reflected, good. But what about the green? Yeah, the green is not. So let me put the other equation on the board, which says that if 2t equals an integer and a half of the number of wavelengths that are in the oil, I would get minimums on reflection. And so I guess I want to apply this one for red light and this one for green light. And so as I apply this, first for the red, maybe I'll even use red for red here. Here's what it says. It says then, according to this, because I can see reflected red light, the thickness must be an integer times the wavelength of red divided by 2 divided by the index. So that would mean it's an integer times 640. And why don't I just keep the units as nanometers? I was about to switch to meters, but there's no other units going on here, so I'll just keep everything in nanometers. And then I'll divide by 2, and then I'll divide by 1.25. And so again, this is saying some integer times, whatever this reduces to, 640 divided by 2 divided by 1.25 is 256 nanometers. So that means I have a whole series of options. It can be 256 nanometers. It can be twice that at 512. It could be 3 times that at 768. It can be 4 times that at 1024. It could be 5 times that at 1280. And I wanted to do enough so you see the point. I really don't know which it is quite yet. I just know that it is one of those, and of course there's an infinite number of them. I will say that even though we didn't get too much into it, since this is just an introduction to our optics, you'll notice that it did say thin films, not just any size film. And so even though technically our math says it goes infinitely, it won't. The math is not valid when it's no longer thin, whatever thin means. But what happens is that if this gets too thick, remember the beam is coming in but the beam is made up of a series of light given off at different moments from different atoms. So there's only a certain length that is what we would call coherent with itself. So it can't be so thick that this first part bounces off and comes back and hits part of a new train of photons. It's got to be the same train of photons to begin with. And so there is what we call a coherence length. But that's beyond the scope of our class.
Why don't you deal with superposition? Because they'll overlap and the end of one is like...
Well, they will overlap, but there's no correlation between that set of photons and that set of photons. And so to get interference, we need to know how does this reflected beam correspond to that one. And then how they correspond is just random. And that's why if you get too thick, you won't see this, which is an interesting discussion in itself, and your author just kind of passed that right up. But many times students will ask, how come I don't see this effect when I look on a glass window? Well, the answer is 1/8 of an inch or thicker. And it doesn't work. That's more distance than the coherent photons coming in. Depending on your light source. You could have a light source that is coherent that long, and then you would be able to see it off of a glass window. But in general, you don't. Yeah.
Should the M's be the same?
The M's the same as what?
Those two M's,
Oh, for the green one?
green and red.
Maybe not the same.
So
But the thinner it is, the more likely they are the same. So no, I'm not saying that they are the same. In fact, if I put my M's underneath it here, this was M equaling 1, this is M equaling 2, this is M equaling 3, this is M equaling 4, this is M equaling 5. So I really have all of those going on. That's why they can correspond to any M over here for the green. But I do know this, that I have to have both conditions met. I have to have a thickness of a certain value that would reflect red and not green. And so we have yet to do this calculation too. What would be the corresponding thicknesses that would give us no green light being reflected? And then hopefully there's only one thickness that agrees with both conditions, and then I can pick out which one I want. That's where I'm kind of headed this. And so changing maybe the color of my pen here to green, I can say, all right, let's look at green light. And so as I go ahead and do my calculation for green light, I would have this. I would have the thickness is, and then I would have an integer plus a half. And then I've got my wavelength for green, I've got the 2, and I've got my index for my oil. Putting that into here, I would have an integer plus a half. What'd they give me for green? 512? So 512, and again, I'll leave it in nanometers. I've got the 2, I've got the 1.25. And so these are the possible thicknesses I can have for green. So 512 divided by 2 divided by 1.25 gives me M plus a half, 204.8. So keeping that in mind, then, for no green light to reflect, what could I have? Well, the smallest one could be M equaling 0, which means then I would multiply by a half. Yeah, guess I don't need a calculator for that one, huh? 102.4. Amazing how lazy we get with our calculators, huh? What is 5 times 5? Oh, wait, I got my calculator. I got my phone right in my pocket. Let me get it up. Yeah. And that one does not match anything up here. It's pretty thin. So yeah, you would get no green from that, but you wouldn't get a bright red from it either. So that's not it. Let me then multiply it by 1.5. That is 307.2. That would correspond to m equaling 1. Well, that doesn't seem to match. Let me go to m equaling 2. So that'd be 2.5 times the 204.8. That's a thickness of 512. Shall I continue, or are we good? We're good. All right, all right. So obviously 512 is a thickness that does work, and it's the thinnest of the thicknesses, and that's probably it. I would suspect we might even have more later on there, but the thickness must be 512. 512 gives us a lot of red light coming off the surface and no green light. And so it would have a lot of red and no green. And that's it for 25. 2 more here. Let's try number 29, and then we'll get started with our last chapter here. But 29, again, more on the thin film here. More of a practical application. I had commented that these thin films can be really nice because they can select colors, one color versus another color. Of course, in this case, we would be thinking about the thin film as giving us information about how thick the oil film is. And so that's another nice reason for these thin films, is you can put your optics on it and measure very small thicknesses by the interference pattern. But the other side of the coin is letting light through or not letting light through, so you can see different colors or take pictures of different colors. And this is a very common procedure because there's a red line, the alpha line is what we call it, that we use a lot to see what's going on in the stars. And that's what 29 says. It says astronomers observe the chromosphere of the sun with a filter that passes a red hydrogen spectrum line of wavelength 656.3 nanometers. It's called the alpha line. Okay? The filter consists of a transparent dielectric of thickness D held between 2 pieces of glass, of luminized glass, so they help with the reflection. But the filter then looks something along these lines. Here is a glass piece, here is another glass piece, and there is a very thin dielectric of thickness D sandwiched between these 2 pieces of glass. That's what they're trying to say here. It says the filter is hopefully held at a constant temperature. More on that in just a second. A. Find the minimum value of D that produces the maximum transmitted light for alpha when the dielectric constant of the index is 1.378. So the index here, 1.378, is used. They don't really say what kind it is. That's okay. We know its optical properties is really all we care about. But an important piece was in the statement that it's sandwiched between glass. Glass can have different indices, I realize, but most of the glasses are at the 1.5. You guys did a lab recently where you measured the index at 1.65, if you remember, for the yellow. But in that area, 1.5, 1.6, up to 1.7, those are our glasses. The point here being the index of the glass will be higher than the dielectric between them. Because that is part of our requirement to analyze this thin film or any double slit. I mean, any single film. So let's go through it again, just like we did in the last step. Let's look at a beam coming down. It bounces off, and this one bounces off. If the thickness, which this time they call it D instead of T, so the extra path length is 2D. If that is equal to an integer number of wavelengths, let me pause again. Integer number of wavelengths where
between glass and
Yeah, in this material. They don't say what it is, so how do you want me to label it? I'll just put in the film, the thickness, the thin part. Okay. But if that path length, 2D, is an integer number of wavelengths, that by itself, I would have expected to get maximums on reflection. Now I'll put slash minimums because as we've done a number of times, we need to now make the next step and say, does that get adjusted because of the phase transitions that take place? So are there any phase changes here? Okay, this first reflection at the top, any phase change? Okay, good, no, how about here? Yes. And so one of them undergoes a phase change, but not the other. What does that mean about our equation? Yeah, instead of being a maximum, as we would have expected just because of path length, it now has the added effect of the phase difference. And so this is the equation to give me minimums on reflection. Yeah, did I miss something?
How do we look at the light?
Oh yeah, now let me make sure very clear. What I've analyzed so far is the light being reflected. And that's the way I do it first. And I would encourage you to find out the equation for reflected light first. Because in this problem, as you're pointing out, we don't want the reflected light. What do we want? Yeah, this, as it's pretty clear, is our astronomer. We do not want to see the light reflected, I don't think. Is this on a lens? Well, it's a filter. So we're going to put it in front of our telescope, and we want it to come through. So we want to maximize the light that is transmitted. All right. But like I said, I like to start with just analyzing this first step and find out, do I get a minimum or maximum for reflection? And then the rest of the equations fall into place. For example, 2D equals an integer and a half would correspond to maximums on reflection. Now again, for this problem, I don't care about the light being reflected, so I'm not going to even worry about those equations. But then, for the transmitted light, and I'll write both of them out here, this equation that was giving me minimums on reflection, the reason it's giving me minimums is the light's not there. Where is the light? It's being transmitted. So this is really the equation that I would want for this problem. I want lots of light, maximum, and I want the lots of the light to be transmitted through the filter into the telescope so we can look at what's happening. The other other three equations, for the total of 4, I'll put here for completeness, but we don't really need them for this problem. So we don't need anything for reflection, we don't need anything for the minimum on transmitted, but this is the key problem for this one. All right, so now coming back over here, I completely have forgotten what the question's even asking here. What is the minimum value of D? So, of course, there's integers that can fit here, and so D, the thickness of this, would be an integer times the wavelength divided by D divided by N. And so the wavelength that we're trying to see... Oh, thank you. Yes, that's a 2. The wavelength we're trying to see is what, 600 and something? 656.3, okay. Nanometers. We've got the T, the 2, I can't get that distance out of my head there. And then the index of that was the 378, yeah. And so the thickness becomes 656.3, divide that by 2, divide that by 1.378, and I get some integer m times 238 nanometers. So there are many different thicknesses, but it does say the minimum. So D minimum here would be 238 nanometers. And so this filter, to be designed right, would, you know, start off, if somebody was making it, a piece of glass, then you would deposit it, I'll say it's a vapor deposit, so you would leave it in the environment in the vacuum for a while and usually cool the glass, and so the vapor would condense on there, and you would probably measure it optically till you got to 238. Then you stop the process, put another glass piece on top of it, and then we have the thickness.
So
Yeah.
E minimum is always at M1, not M0.
I wouldn't say always, because if I was dealing with this equation,
I'll put M0.
I could get a smaller value of D when I put in 0. If I put in a 0 for this one,
0, 0.
I get a 0 thickness, but it was also what I would get for any and every other color too. So it wouldn't really work as a filter. Yeah, and you can imagine, right? If you squish this together, so it really wasn't there, 0 thickness, the green light would go through, yes, or excuse me, red light. The red light would go through, sure. But so would all of them, and so it's not going to function what you would want. So that's why I'm skipping the m equals to 0 this time. But I may not skip it here. And I think the next problem actually, we have that issue. Yeah. And so there's my alpha line. And it gets a little bit better than that here, because again, here's one of the challenges of these thin surfaces here is, notice the color or the wavelength that gets transmitted is highly dependent on that thickness. So in this case, B says, well, what if? And this will take us back a little bit to our thermodynamics here. What if the temperature of the filter is increased? Now they go on to say, go ahead and assume the index doesn't change with temperature, which is probably not completely true. But let's just say it doesn't. Anything else change? The separation between them, right. And so these filters are very temperature dependent because they are affected by their distance, and their distance is affected, of course, by their temperature. And so the filter works really well at a defined temperature, and you get off of that a little bit, things start to change. And you're going to have to make some adjustments for that if you are the scientist here trying to look at that and figure out what's going on. And that's the whole part of B. It says, what if the temperature of the filter increases above its normal temperature? What would happen to the transmitted wavelength? And so maybe coming back to here, you can see that if we let it warm up, then doesn't D become bigger, which means the wavelength that comes through is a little bit bigger. And so we would no longer be filtering for the right wavelength that we thought we were if we let the temperature get up. And that's what you want to do. Yeah?
Does like the D get shorter because the glasses, they get bigger?
No, well, no. This, actually, I'll take us back to our thermodynamics. Here I have a piece of metal, I have a hole in it. I warm it up. Does the hole get bigger or smaller? Yeah, we get bigger. So it doesn't just move in, the circumference gets bigger too. And so if I had a glass piece that looked like that and had some material in here and I warmed it up, everything would get bigger. The little dielectric between there would get bigger, I'll exaggerate. The glass piece on top would get bigger. And so yes, everything gets bigger, and including the space in between them. Yeah. And so it would expand a lot in that picture. Oh, was there a C on this? C. C goes on to say this dielectric will also pass another near visible wavelength. What color is it? Because again, if you're trying to take a picture of the sun and you're trying to see where the hydrogen is and how much concentration of the sun or the chromosphere of it or any other star, we would like to see just the light coming from hydrogen. And this is a great filter because it lets just the light given by hydrogen come through. It tells us where it is. Unfortunately, the way we've designed it, it's going to let other near visible light through. Because if we use this thickness and we rewrite this equation says the wavelengths then that come through are 2ND, and maybe I should put C here, 2ND divided by M. And so if I put in my numbers, hopefully my 2ND is the 656 that we got before. So 2 times 1.378 times a thickness D of 238, I get my 656.3 nanometers divided by M. And so these are the wavelengths that would come through on this filter. And so obviously when M equals to 1, we get a wavelength of 656.3. That's not a surprise. That's how we designed this thing. We designed it with just the right thickness so that this light would come through. That was the point. But when M equals 2, we can get a wavelength also that would come through. This would correspond to the down and back of being 2 wavelengths. So it's going to be a smaller wavelength. And so if I take that number and divide by 2, okay, 600 and, is that 28? 5, 25, 3, 28. Yeah. 300. Thank you. 328. Yeah. So 328 nanometers. And not really would I call that visible light. That's way out, or not way out of the visible, but it's beyond the visible. And so we're in the ultraviolet, which is why this is a problem, because a lot of light coming from our sun and the stars is like that. On the other hand, we got to stop that because we're trying to see the hydrogen, the red line, and yet this gets through. So I think they said that you put another filter to block that, don't you? What does it say here? The dielectric will pass what near visible. One of the glass plates is colored to absorb that. So in addition, you put some coloring in here that will be like a red tint to it. So it lets red through, but it doesn't let the blues, and in this case, ultraviolet in. And so the violets and the ultraviolets get blocked. Some of your cheap filters don't do that, which I've heard sad stories of people looking at the sun through these filters. Because it blocks everything out, it really dims the sun, it just gives you the red color. And it's really neat to see, because you can see all the red colors and the hydrogen from it. But at the same time, if you're not careful, you get a lot of ultraviolet in, and so, which is the whole reason you're not supposed to look at the sun, because the ultraviolet does damage your eyes.
So you're concentrating.
So, yes, and isn't that how Galileo went blind? Because he didn't know that. He built a telescope, looked at the sun, noticed the sunspots, and went blind. So, but he got to see it, right? That's right. And then one more. What number was this? 29. Let's do 50 and then get started with the next chapter here. 50 is, again, a double slit, a little more complicated than any of the ones we did, but it does have the integer and a half one. And so I thought it would be a good one to do. It also has a little practical side on our spectroscopy here, or microscope, I guess I should say. What did I say, number 50? Okay, so here's one of the challenges with a microscope, is that if you look at cells, they're often transparent. So how do you see them? And they'll do this by interference. And so the problem starts off by giving the reason for the problem, and then the problem's a little bit different. It's not quite as complicated. But it says here, many cells are transparent, they're colorless. The structures of great interest in biology, medicine can be practically invisible to the ordinary microscope or microscopy is the process, I guess, of using a microscope. To indicate the size and the shape of these cells, we would use interference and the difference between the refracted as they shifted in the interference pattern. So somewhere in here they go on, let's imagine this as an air wedge. Here's the problem. An air wedge is formed between two glass plates that is in contact along one edge and slightly separated along the other edge. So this is a lot like the problem, and this is why I grabbed it, what I was showing you last time. I took the glass plate, I set it on there, and it was kind of wedge shaped in there. On my case, I just had dust on there. Sounds like this one is a little more careful because one edge actually touches. And so on this one, we actually have glass touching on glass. Whereas I think I told you last time with mine, it was impossible for me to get rid of all the dust. So I just set it on there knowing that the dust would be of different sizes and I would get kind of a wedge shape. But this one is starting off by saying, let's take a piece of glass and set another piece of glass so that the two edges of the glass are actually touching it. And so here it is. An air wedge is formed between two glass plates in contact along one edge and slightly separated on the opposite edge. And of course, my picture shows them a lot separated, so I can draw in there, but obviously these separation and these wedges are going to be just, a fraction of a wavelength of light, or I shouldn't say fraction of a wavelength, but many wavelengths of light, which is a very, very small distance nonetheless. It says, so when the plates are illuminated with monochromatic light from above, the reflected light has 85 dark fringes. All right. So let's talk about that. The light from above is going to come down, and we made the glass plate really, really thick. So we don't get an interference from the glass plate. I want to emphasize that. Remember, we get an interference from our thin films. We talk about how the light has to be coherent. So it only works when they are kind of thin. So not going to worry about the reflection off of here. The one that's of interest to me is the reflection off of there. That and the one below it. And for our last time, before we go to the next chapter, let's work this out again. What if twice the thickness is an integer number of wavelengths in the film? Well, my first reaction is if that's an integer number of wavelengths, I would expect to get maximum light on reflection. But let me put the word minimum right next to it because it may not stay as a maximum on reflection until I begin to look at also the phase changes. So, is there a phase change here? Well, what is our filled with? I think it's filled with air, right? Yeah, see it says an air wedge. An air wedge is formed between these two glass plates. So as I come over here and realize then the index in here is a 1 and glass is up about 1.5 and 1.5 here, then this reflection, no phase change, right? It goes from a high index to a low. How about this reflection? Yeah. And so I'll circle it in red. But the point is I've only done one circle. And so what I would have thought came out to be bright light or maximums now becomes minimums. And again, that's where I like to start. I like to start looking at the light that is being reflected and in an integer number of wavelengths. And then we could write out the other equations if we want. We could write out that if 2t equals an integer and a half of wavelengths, then I would get bright light reflected. And in the interest of time, let me not write out all of them because I don't think we need transmitted. I don't even think we need the dark or the bright spots, because doesn't they say dark spots? Yeah, it says when illuminated with monochromatic light from above, we get 85 dark fringes. So what we are going to be interested in is minimums and reflected. And so this is the equation for this particular problem. Now, why are there fringes? Why are there these stripes, if you recall from what we saw last time, of dark? Yeah, the thickness keeps changing it. So in other words, there is some point in here where the thickness would correspond to m equaling 1, and then m equaling 2, and then m equaling 3, and then m equaling 4. And so taking the information that they have told me so far, I would say 2t equals what? Well, where would I see the first dark fringe? I guess I'd actually see it with a thickness of 0, right? And we don't have the issue before where we have all the colors, but this is just one color coming in. And the light that would come right here at the edge, you could say that the second beam barely traveled an extra distance, so the thickness is 0. But there was a phase change. So as you look from above, you will see right where it makes contact, that edge of the piece of glass will be dark. And then as you move over, it'll go bright, and then it'll go dark again. That next dark one would correspond to M1, right? Because M equals 0 would be the first one where they're in contact, 0 thickness. So if they say you see 85 bright ones, this is what I wanted to point out. This was your question earlier, Lester. 85 dark fringes means that if I label this as the maximum thickness, way over here, maximum thickness, then I would put in the 84 for the value of m. Because again, it's not an 85, it's an 84. Why? Where's the first bright one? M equals 0. So we have 0 to 84. That counts as 85 fringes. And so don't miss the counting sequence there. And so I've got 84 lambda over 1. And I don't think there's much I can do because they didn't give me the wavelength, right? So I'm kind of stuck there with solving for anything. I can't get the maximum thickness. I can't get the wavelength. They need to give me one of those two to find it. So let's keep reading. But at least that's the information they've given me so far. It goes on to say, calculate the number of dark fringes that will appear if now we run this experiment underwater. So that air pocket, the air wedge, now becomes a water wedge. Well, same logic though. What would change now if we filled this whole thing with an index of 1.33? Would it change our equation? Would minimum switch to maximums or anything? No, we'd still get a phase change. So we filled it up with a fluid that doesn't give us enough to affect our phase changes. So our logic that came up with the dark places, the dark fringes, is still valid. All right, but our index has changed. So when we come over here to write it, we would have 2 times the maximum thickness equals to some value m, would it, maybe I should have paused here, would anything have changed? We filled it with water?
Would it still touch on the very?
Would we get more fringes? Less fringes? Well, let's see. Why are we even getting an interference? Isn't it because of an integer number of wavelengths? So essentially by filling that up with water, aren't we essentially making the wavelength smaller? Which means if we were getting a dark spot right at this location, let's say this picture corresponds to m equal 1. The reason we get a dark spot here is because this down and back is, say, a half wavelength. Quarter wavelength, excuse me, because there's a phase shift. So if this thickness was a quarter of a wavelength, then down would be a quarter, back up would be a quarter. That would be an extra length of a half, plus the extra phase shift it did would put constructive, bright spot. Sorry, I was saying it right the first time. All right, let's try it again. If this thickness was a half wavelength, if this was a half wavelength down and half wavelength back, the path difference would be 1 wavelength. Then the extra phase shift would make it equivalent of 1.5. They would be out of phase and you would get a dark spot. So the reason you're getting a dark spot here is because this thickness is a half wavelength. If you now have a shorter wavelength, wouldn't that pattern show up here then? And so the dark fringes that was here is now at a lower thickness. So the 85th one that was here would now be here. And so we should have more. We shouldn't have the same number. We shouldn't have less. We should have more. And so let's see what that comes out to be. What is the value of m now that our wavelength has changed? And so I'll just write that as an m and then write this as a lambda over 1.33. If I then put the lambda over here, I get 2 times the maximum thickness over lambda times 1.33 is equal to m. This ratio I do know from the first experiment. So m equals 1.33, that number. The 2, actually I could just put the 2 together. Why don't I do that? I'll group that together. Because as I look at this, the 2t divided by lambda is 84. And so my new integer here would correspond to 1.33 times 84. And that's pretty close to 112. And so m equals 112. Now let me ask, how many fringes do I see? 113, right? Because we would be counting the first fringe of m equals 0. And so it would be 0, 1, 2, 3, 4, 5. And so I think that was the question, how many fringes, not the order, right? Replaces. Calculate the number of dark fringes that would appear. All right, well, there's some more interesting problems that we will have you work on the homework this weekend. Let's go, not much time here, to the next chapter and see how much we can get started with the next chapter. And then we'll just have to call it quits after Thursday and say, well, that's unfortunate and got to keep telling myself this is an introduction to optics and there's so many neat things that we could do. Well, we just save the hard ones for the test, I guess. No? All right. But let's take a look then at least what this chapter begins to. So in the 20 minutes we have left, it's about perfect timing to kind of give us the the first piece of this chapter. But again, let me describe it this way. That keep in mind that light is waves, and we're going to look at the interference of our waves. And so just like we've been doing in chapter 37, we're going to continue that. And in fact, chapter 38 looks at 3 ideas of our interference. The first one is what we call diffraction. After that, we get to the diffraction grating. And after that, if we have time, and hope we can at least touch on it, we can get to polarization. And so those are kind of the 3 big topics. What we'll just do here today in the 20 minutes is set us up for diffraction. We actually saw this already. Anybody remember what diffraction is? Yeah, it's this spreading of the light as it goes through a single opening. Let me see if I can show you that. I'll turn the lights down again, and just like we did last time, let's look at a laser beam on the wall, and let's take, hopefully let you guys see it, but here is that slit again. It is pretty small. I don't know, can you see even a shadow on the screen there where it kind of goes through? Small opening. And so if I take a small opening and shine it through here, you will hopefully see the light spread out. And now, let me draw your attention to, does it spread out evenly? Aren't there patterns, like right in the center, it's really bright, then it goes dark and goes bright and dark and bright again? So we have a kind of this fringe pattern from the single slit, kind of like we had for the double slit. It is a little different. What we did last time, just to make sure it's clear, is I squeezed this together really tight. And I'll squeeze, And I tried to show you that if this thing was really, really narrow, you would get light that spreads out almost equally in every direction. Of course, you can even see in mine that it is bright here in the center, and as I go to the left or to the right, it kind of fades out. And so, why does this light spread out? What's the equation for the spreading of this light is the first question here. And so, just like we did for the double slit, let's also look at the single slit. So, I'll start with a picture from your textbook, and actually I'll go to this folder here for the pictures because I like them. They're a little bigger and easier to work with than that PDF file here. But as I call up this first picture, or picture number 5, I guess I should say, is your author says, let's take a closer look at this single slit. And he says, all right, here is the opening for a single slit. It is not really infinitely thin, is it? I hopefully you saw that if it was infinitely thin, it would kind of spread out equally. And that's how we analyze the double slit. But we need to change that a little bit. We need to modify that. And this is what your author is trying to say. He says, look, take a single slit, and just so that we don't confuse the size of the opening with the double slit, what notation did we use for the spacing on the double slit? D. And so the A is the size of the single slit. All right? And your author says, how are we going to do this? Well, let's look at the wave that comes through here. Maybe I'll even change colors here. But we might get away with it the same way we got away with the double slit. Because if you think of this upper part of the screen as being infinitely thin, and then the next one being infinitely thin, and the next one being infinitely thin, and the next one being infinitely thin, and the next one being infinitely thin. And of course my drawing gets kind of messy, so that's why I like what your author has here. He says, look at this. What are you going to see on the screen? You're going to see light coming from what we would call the bottom of the opening, then a little bit higher in the opening, then a little bit higher than that, and a little bit higher than that, and a little bit higher than that. Now he chops the screen into only 5 pieces. But can you see how you could do a calculus on here? You could chop this into an infinite number of pieces and add them together. Because again, we saw, at least by experiment, that when they get infinitely thin, they spread out equally. And so your author says, let's just analyze this as we did for the double slit. It just has an infinite number of slits. They are microscopically close together, and they are microscopically thin. And so we probably won't get a chance to do too much calculus today. In fact, we probably won't at all. We'll just kind of have to sweep that under the rug and say, here's the results of all the adding these up here. But we can at least get started by saying, what would I kind of expect to see off here to the side? Wouldn't you kind of expect to see times where they add up in phase, so they would be bright, and times where they don't add up in phase, so they would be dark? And isn't that what I just showed when we went through the single slit? We saw bright, dark, bright, dark, bright, dark. And so in that sense, it's kind of like the double slit. But the double slit, we only had to add 2 waves together. This has an infinite number. So we do expect it to be a little different and mathematically harder. And like I said, we'll kind of cheat on the mathematical stuff and just get the answer here. But well, at least conceptually, we should realize there is something more going on. So it should look kind of the same, but not exactly the same. That's my beginning point. I expect to see fringes, and you do. I expect to see them kind of like, but not exactly like the double slit. And you do. That's the point. And so let's talk about this. For example, let me change my picture, since I kind of got that one a little messy here. Let me come up here and say, I'm just debating if I should draw mine down, because I did the double slit down, and I want you to see how it's kind of the same discussion, but he's got his up. Doesn't matter? All right, I'll draw it up then. All right. Okay, so let's look at the light coming from here, and then let's look at the light coming from the last one. Only those two for a moment. Doesn't this look a lot like the double slit? I mean, for the double slit, didn't we then draw across here and say, okay, that's perpendicular. This is the opening, which now we have an A instead of a D. But isn't this the extra path length? And isn't that equal now to A sine theta, just like it was for the double slit? Except, of course, we had a D instead of an A. Okay, and then that's kind of what your author is saying, although he's kind of broken it to the next step here. So I thought this picture might be nice to see before we talk about that one here. But this is saying that the extra length, and I want to emphasize, it's the extra length of the bottom one compared to the top one. Aren't there a bunch in between? Okay, so again, I'm only looking at the top and the bottom one here for a moment. But as long as we're talking about it, what if A sine theta equals an integer number of wavelengths? Well, we did this for the double slit. What did we say for the double slit? If the distance was an integer number of wavelengths, what do we get? We got a bright spot on the screen. Will we get that here? Will this come out to be a bright spot? And I think your first reaction is, well, yeah, because this one and this one add up in phase. But that's not the whole story. Because what else is going on? Yeah, the other ones. In fact, let me just draw one of a different color down the middle. Look at that one. So this would be half of that one. Oh, so how would this middle one compare to the top one? What if you put those two together? They'd be out of phase. And what would that give you? Dark. So see how this extra set of beams kind of just throws off our logic for the double slit? The double slit was easier. It was just two beams. We just asked, was the two beams in phase or out of phase? See, what I have now is a bit more complicated. And I would do it this way. I would say, let's look at this first beam and the middle one. Let's think about those two together for just a second. Then after we do that, let's think about one that is just microscopically below the top one and microscopically below the middle one. How would those two add up? They would be out of phase also, right? Okay, and then we can continue this pattern here and here. How would those add up? Yeah, they would cancel, right? And so if I were to add up every single wave, what would I get here? They would all cancel. So what should this spot on the screen give me? Dark. Minimums. Did you catch all that? Because if I go back over here to the double slit and I put d sine theta equals an integer number of wavelengths, would that give me the location of the bright spots or the dark spots on the screen? Bright. And so we just had to add up those two beams. Those two beams were in phase. But when we have an equation that looks a lot like the double slit, we don't get bright, we get dark. And so I think one of the hardest things to keep straight on the test is that this equation, which looks a lot like this equation, is different. This is for the double slit. This is where you get bright spots. This is for the single slit, and this is where you get dark
But how
spots.
did you know that they're out of phase? How did you know that you are dark spots?
All right, let me run through it again.
Oh, I'm sorry.
If the first and the last are this far apart, okay, which again, the first and the last, by themselves, you would say they are in phase. That's how we got exactly, that's how we got this equation.
Oh, okay, so you
But what's different is we're adding up an infinite number. And so out of phase, 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 out of phase. And so instead of actually adding them up yet, I can tell you that that equation is a place where I will get my dark fringes. It does, as you can imagine, get a bit more complicated than that, because although this might be true for m equaling 1 and m equaling 2, be careful here. Would this work? Would this logic work down the middle? See, down the middle, that one would be in phase with that one, and we are essentially saying they're all traveling the same distance. So what I just reasoned out makes sense above or below the center point. And so this is true when m equals 1, 2, 3, or even -1, -2, -3, but it is not true for m equals to 0. And yet, when we did the double slit, what were our values of m? 0, plus or minus 1, plus or minus 2, plus or minus 3. Because we could get bright spots down the center as well as off. So again, just as a starting here, be careful with this single slit. The single slit is a bit more complicated. You can see why we wanted to talk about the double slit before the single slit, so that you had something to build on. And we wanted to see how they are so closely tied together that it is very easy for students to confuse the two. Okay? And so I'll point it out that that has a D in it, that has an A in it. That is for the single slit. This is for the double slit. This gives us the location of bright spots. This gives us the location of dark spots. And M equals to 0 is down the center is bright. So the M equals to 0 doesn't work for calculating where the dark spots are. But the M equals 0 does work over here for calculating where the bright spots are for the double slit. It's why your author then says, let's take a look at this intensity pattern. For you guys, maybe it's best if I just shine the laser here again over on this wall, and I think that'll be dark enough. If I just send the laser beam through oops, wrong one, right there. Maybe it's not. I don't want to turn this off though. We only got a few minutes. But can you kind of see how it's bright in the center? And then there's a dark, bright, dark, bright, dark, bright, dark, bright. Well, that's probably the last I can see. But there is a whole series of dark positions. And again, this equation gives you the location of those dark spots. Keep that in mind. In fact, without much proof, but as we're just kind of wrapping it up here for today, let's look at the next graph your author gives you. At number 6 here, he says, this is what it should look like if you shine the laser beam on the wall. Well, I did. What you should see is it bright in the center, fading away, and finally gets dark. This dark spot would represent mathematically to an angle of m equaling 1 on one side and m equaling -1 on the other side. And so then it would get bright, then it would get dark. Oh, but did you also know something else a little bit about this? Right, as we go from bright, dark, bright, dark, bright, dark, each bright is not as bright as the one before. You see, we didn't say that back here for the double slit. Back here for the double slit, what did we get for the equation of the intensity? Yeah, it was cosine squared of phi over 2. And of course, the phi was the phase between the first one and the second one. And that's all we had to work with. So there was no question about what the phase was. But this indicated that the bright spot should be equally as bright. That is not what is happening here. And in fact, your author has plotted the intensity up here to show you where is most of the light. Down the middle. And then it gets less bright until you get to m equal plus or minus 1. Then it gets bright again, here and here. Then it gets dark again. So each of these dark locations correspond to a phase difference of either pi, 2 pi, or 3 pi. But also, again, notice the intensity pattern drops off. And so, since we're at the end of today's lecture, let me just give you the final results of this calculation. Remember, we spent some time getting this. This pattern is obviously a bit more complicated, because what we would have to do is we would have to add up an infinite number of waves. And so we could take our calculus and take the slit infinitely small and then add them all up. Your author chooses not to actually do the calculation, and since we are low on time, that's probably a good choice on the author's, because I'm going to follow that. I'm going to say, what is the equation for the intensity of a single slit? You might expect it to look a little bit like this. Fair enough? You would expect it to be some kind of intensity down the center. Okay, so he puts down the center. You might also kind of expect this trig function to be here, except didn't the bright spots and dark spots kind of change their roles here? So, yeah, not a surprise. We're going to see a sine instead of a cosine. And so we get our phi over 2 again. However, what's not so obvious is an added piece. You see, for this one, we were just adding 2 waves together. And so the fact that they were a cosine to a sine. That makes sense. But it actually diminishes in intensity according to, and without proof, and to finish for today, it'll be the phase over to there. And so this little function, sine x over x, is referred to as a sinc function. And I know that mathematicians love to put this in your calculus class. I bet you did one of these like limits. The limit is sine x over x. No? Is 1, exactly. Sine x over x. And anyways, but at the straight through, the limit as sine x over x goes to 1, you get an intensity down the center of just the center intensity. Well, we'll stop there since we're past time, but this is where we'll pick up and put closure to it on Thursday.